Welcome to today's class on measure and integration. Today we will discuss a theorem. The statement is the outer measure of an interval equals its length. Proof. Here actually we want to show that m star of I equal to length of I. That is outer measure of an interval equals its length, right? Here I is an interval, so it may be a closed finite interval, or it may be any finite interval, or it may be an infinite interval. So we will prove this theorem by three cases. So first case is, let I equal to closed interval AB, that is I is a closed finite interval. So let epsilon greater than 0, then clearly we have I is contained in A minus epsilon by 2, B plus epsilon by 2. So suppose that this is AB, suppose that this is the interval AB, then here is an A minus epsilon by 2 and here is a B plus epsilon by 2. Then clearly we have I is contained in I equal to closed interval AB is contained in open interval A minus epsilon by 2, B plus epsilon by 2. So by the definition of the Lebesgue countermeasure, we have m star of I is less than or equal to length of the interval A minus epsilon by 2, B plus epsilon by 2. Here actually the length of the interval A minus epsilon by 2, B plus epsilon by 2 is actually B plus epsilon by 2 minus of A minus epsilon by 2, that is minus A plus epsilon by 2, and which is actually B minus A plus epsilon, that is epsilon by 2 plus epsilon by 2 is actually epsilon. So here we have length of A minus epsilon by 2, B plus epsilon by 2 is B minus A plus epsilon. Here epsilon greater than 0 is arbitrary, so clearly we can say that m star of I is less than or equal to B minus A, which is equation 1. Now let collection In be a countable collection of open intervals which covers I. Then here we can apply the Hain-Borel theorem. Hain-Borel theorem says that if A is a closed bounded set in R and A is contained in union over alpha element of I G alpha, where the sets G alpha are open and I is some index set, then there exists a finite subcollection of the sets, say set Gi where I is from 1 to n, whose union contains A. This is actually Hain-Borel theorem. So here collection In is actually a countable collection of open intervals. So by the Hain-Borel theorem we can say that there exists a finite subcollection of collection In which covers I, right? Borel theorem, there exists a finite subcollection of collection In which covers I, right? Now we will show that sigma length of In is greater than or equal to B minus A for this finite subcollection. This is because the sum of the length of the finite subcollection is not greater than the sum of the length of the original collection. It suffices to show that sigma length of In is greater than or equal to B minus A for this finite subcollection, right? So here A is an element of union over n In implies that there exists an open interval in the collection In, say A1, B1 that contains A. Clear? That is, here A is an element of union over In. So clearly we can say that there exists an open interval A1, B1 in this collection In which contains A, that is A1 is less than A less than B1, which is taken as equation 2. So if this B1 is less than or equal to B, then clearly we have B1 is an element of closed interval AB. That is, here we have A1 is less than A less than B1, right? That is A1 is less than A less than B1, and if this B1 is less than or equal to B, clearly we can say that B1 is an element of closed interval AB, but B1 is not an element of open interval A1 B1, right? So There exists an interval a2 b2 in the collection In such that b1 is an element of a open interval a2 b2, right? That is a2 is less than b1 less than b2. Okay. In this way we get interval open interval a1 b1 open interval a2 b2 etc. open interval ak bk from this collection In such that ai is less than bi minus 1 less than bi, right, which is equation 3. Since this collection In is finite, this process must terminate with some interval ak bk, right? Terminates fully if b element of ak bk, right? That is if ak less than b less than bk, which is equation 4. So sigma length of In is greater than or equal to sigma I from 1 to k length of ai bi. Here open intervals ai bi's are actually the intervals in In. So clearly we can say that this summation of length of In is greater than or equal to summation length of ai bi. This summation is actually length of a1 b1, right, length of a1 b1 plus length of a2 b2 plus etc. plus length of ak bk, right, ak bk. But we know that length of a1 b1 is actually b1 minus a1 b2 minus a2 b3 minus a3 etc. So this is actually bk minus ak plus bk minus 1 minus ak minus 1 plus etc. plus b2 minus a2 plus b1 minus a1, right, which can be written as bk minus of ak minus bk minus 1 minus of ak minus 1 minus bk minus 2 etc. minus a2 minus b1 minus a1. Okay. So by equation 3, which is greater than bk minus a, right, equation 3 is actually ai less than, equation 3 is ai less than bi minus 1 less than bi. This is equation 3. So from 3 we get this expression is greater than bk minus a, and which is bk minus a1 which is greater than b minus a. This is by equation 2 and 4. Equation 2 is actually a1 less than a less than b1, right, a1 less than a less than b1. This is equation 2. And equation 4 is ak less than b less than bk. This is equation 4. So comparing these two equations, equation 2 and equation 4, we get bk minus a1 is less than b minus a. So here sigma length of In is greater than or equal to b minus a. So clearly we can say that m star of I is greater than or equal to b minus a, which is equation 5. So from equation 1 and 5 we get m star of I equal to b minus a. Equation 1 is actually m star of I is less than or equal to b minus a, and this is equation 5. So from 1 and 5 we can write m star of I equal to b minus a. That is the outer measure of the interval, that is the outer measure of the closed finite interval I is actually the length of that interval. That is the result is true for the case 1, right. Now we will prove case 2, that is I is any finite interval. So let epsilon greater than 0, then clearly we can say that there exists a closed interval j contained in I such that length of j is greater than length of I minus epsilon, right. Suppose that this is the interval I, then clearly we can say that a closed interval j is contained in this interval I, satisfying the condition that length of j is greater than length of I minus epsilon, right. So length of I minus epsilon is less than length of j, but length of j is actually m star of j because j is a closed interval, finite closed interval. So by case 1 we have length of j equal to m star of j. Here j is contained in I, so by monotonicity we have m star of j is less than or equal to m star of I. And clearly I is contained in I closure, so m star of I is less than or equal to m star of I closure, which is again by the monotonicity. And we know that the outer measure of a closed interval is length of that interval. So this is actually length of I, and the length of I closure and length of I are same here. So m star of I closure is length of I, right? That is, here we have length of I minus epsilon is less than m star of I, which is less than or equal to length of I. We know that length of I minus epsilon and length of I are equal because length is translation invariant. So from this inequality we have m star of I must be equal to length of I. So in the second case also we have proved that the outer measure of the interval I is equal to the length of I if I is any finite interval, right? The third case, that is I is an infinite interval. Let k be a real number, then there exists a closed interval j contained in I such that length of j equal to k. That is, there exists a closed interval j in I satisfying the condition that the length of that closed interval equal to k, right? So m star of I is greater than or equal to m star of j since j is contained in I. But here j is a closed interval, so the outer measure of j is equal to length of j. So which is equal to length of j, and length of j is k here. So here we have m star of I is greater than or equal to k for any real number k, right? So m star of I is greater than or equal to k for any real number k means that m star of I equal to infinity, and which is equal to length of I because I is an infinite interval. So in the third case also we have proved that m star of I equal to length of I. That is, the outer measure of an interval equals its length. So this is the proof of this theorem.